Welcome to the Azure Cosmos DB Essentials Series Season 2. My name is Mustafa. I'm a product marketing manager for Cosmos DB, and in this episode, we're going to discuss partition strategy and how to choose a partition key. So, if I'm a developer, maybe it's my first time working in Cosmos DB or a NoSQL database in general, I go into the portal, I create a container, and then I'm hit with this mysterious partition key. So what's going on behind the scenes in Cosmos DB that needs a partition key? Well, what's happening behind the scenes is Azure Cosmos DB is a distributed database. And the way it scales is rather than trying to scale a single node from 1 core to 2 cores to 3 cores and higher, we just go and spread that workload across multiple nodes, all the way up to all the available nodes on Azure if you'd like. This allows us to scale for all intents and purposes to infinity. Now, when we start to discuss how this affects our partition strategy, this is best understood in the context of this scenario. Let's say that if I want to scale a workload across node 1, node 2, and node 3, and let's say I store my yellow data on node 1, my green data on node 2, and blue and purple data on node 3. Later, when I query looking for my purple data, if I route the query to node 1, it's going to come back and tell me it never found what it was looking for because that data is, as we see here, on node 3. A partition key is a placement hint for the query engine, telling Azure Cosmos DB how to route the data when written, as well as how to find that data when you do a follow-up read. The next question you might have is, can we run queries without the use of a partition key? And the answer is yes. So let's say we have some query, something general that says select X from Y, where Z, and I want to find all of my purple data on node 3. In the absence of a partition key, we actually can solve this problem, which is to run something called a fan-out query. What a fan-out query does is node 1 and 2 will know that they don't have any relevant data in their index, and so node 3, knowing that it does have all the purple data here in its index, will return all of that purple data. Now, the next question you might have is, but if fan-out queries can still find the data, why don't we recommend always running fan-out queries? And the caveat to fan-outs is that they don't scale. So let's say hypothetically each node can support 10,000 requests per second, and I want to scale that up to 20,000 requests per second. We should just split the 20,000 load between the two nodes. Fan-out queries do not distribute the work of looking for data. They just ask every node if it has it. This means we're back to a bottleneck situation, where we're bound by the maximum amount of throughput on a single node. Now, the improvement on this design is the introduction of the partition key. We constantly, across all cloud services, see the word scale on everything. Now, there are 3 things we can scale in the context of a database: reads, writes, and storage. So let's go through the scaling of each. Starting with storage, it's really the easiest to scale. To scale storage, I store my data across, let's say, X nodes with no routing and just run fan-out queries. Now I've scaled storage. But the bottleneck becomes reads, because we now need to ask every node where our data is in order to find it. If we want to scale reads, I can simply replicate my data across each of these nodes. Now it's not only stored all over the place, but since there are copies of my data across all of these nodes, it's actually easier to find. But now writes become the bottleneck, because we have to write so much data in order to be able to read it. So let's try and scale writes. The only way you can scale write throughput is to shard or partition the data. That means we divide up the write workloads so that the writes on node 1 are separate from the writes on node 2. If we remember that we replicated to scale reads, well, now we also have to write the replicas for each of those writes on other nodes. So writes is actually the hardest thing to scale. But back to our original point, we've got a bunch of traffic. Rather than having every request fan out to every node, a better way to design the system with scalability in mind is to route requests only to their minimal number of relevant nodes. And that's effectively what the partition key allows us to do. It gives us a signal. So for a more concrete example of this, let's say that I'm building a shopping cart, and my shopping cart, I typically run queries based off of a user ID. So let's say Alice here wants to know what's in Alice's shopping cart. Bob wants to know what's in Bob's shopping cart, and Carol wants to know what's in hers as well. What we can do is we can set the partition key to the user ID. That way, when we see in the where clause of a query, a where user ID, it equals, let's say, Alice. If Alice is the purple data set, we know exactly how to route to the machine hosting Alice's data. Now, with this idea of scale and partition keys as a placement hint in mind, let's talk about some of the best practices for choosing a partition key. So there's a few design principles when choosing a partition key. First, you need to understand the ratio of reads to writes for your application. Now, if your application is 90% reads, then your partition key should optimize for the top most frequently run queries, allowing you to efficiently route frequently used keywords. If your application is write-heavy, you should choose a partition key that prioritizes load balancing overall request volume. And third, if your application needs ACID transactions, then you should also be concerned about the scope of your partition key, but we'll discuss that in a future episode if you guys want to know. This is typically done in a minority of use cases. So let's go through each of these. If we remember one of the first principles, that a partition key should load balance overall request volume, this is because we want to avoid hotspots on a single node. If I have 20,000 requests per second and I choose the incorrect partition key resulting in one node running at 100% utilization and the other at 0, this will bottleneck the throughput of our database to the power of a single node, which is what we don't want. A good example is an IoT application with the partition key of current time. That is a bad key because if all these devices send a health pulse at the same time, we'll just rotate each node in our network being swamped one after the other as 10,000 devices all ping one node routing by current time ID. A better key would be to route by using device ID as the partition key, because every device has a unique ID, and so each node can serve the message from the device ID or IDs which it should be routing for. This is how you optimize for a write-heavy workload. Now, if we remember our other principle, for a read-heavy workload, we want to be able to route for efficiently run queries. If you balance your overall request volume and just make every request its own partition key, so every write has its own unique partition key via something like a unique GUID, which is the primary key of a document, this is not at all intuitive to query, but you will effectively be able to load balance. Now, on the other end, if everything has the same partition key, you'll be able to effectively query, but you won't have any load balancing at all. So to best do this, you should look at your most frequently run queries, and typically you'll find something in common between them, which should then lead you to your partition key. So if we once again revisit the IoT scenario, to find the best partition key here, I might look at the top most frequently run queries. If in the where clause of my most run queries, I keep seeing the device ID show up, then this would be the right partition key for my use case. All right, so that concludes the third episode about partition strategy and partition keys in Azure Cosmos DB. Tune into the next episode on schema design to better understand data modeling.